We have an example problem here. A 5 nanocoulomb point charge is embedded at the center of a non-conducting sphere, radius of 2 centimeters, which has a uniform volumetric charge density of negative 88 nanocoulombs per meter cubed. What is the magnitude of the electric field at a point that is 1 centimeter from the from the center of the sphere? All right, so I'm going to draw a picture representing my point charge in the middle. So I'm going to call that one Q1. So 5 nanocoulombs. It is embedded at the center of a non-conducting sphere. I apologize, that's not a very pretty sphere. I'm using capital R because I'm using this to represent the actual charged object. So this sphere that I've drawn is going to be my Q2. But I don't know the actual charge. They gave us a charge density. So I'm going to call that row 2. Even though there's not a row 1, I just mean the second object that is charged. But I know this is row for 2 reasons. One is that the problem told me it was a volumetric charge density. The second reason is because of these units. Nanocoulombs is for our charge, meters cubed is a volume. All right, so we are wanting to find the electric field. Let me get a different color back. We want to find the electric field essentially half of the way out. We want to find the electric field. This lowercase r that I'm drawing represents the 1 centimeter. Because it is asking us for the magnitude of the electric field at a point that is 1 centimeter from the center of this sphere, this actual charged object. All right, so spheres, Gauss's law works beautifully. Let's choose a Gaussian surface to have the same symmetry. We need our Gaussian surface to be centered on the point charge and this other sphere, which I'm not doing a very good job of drawing my picture. So this purple sphere is my Gaussian surface, my closed surface that I am talking about the flux through. Okay. So the flux, because we have the right symmetry going on, the flux is both E times A and Q in over epsilon naught. We're looking for E. A is the surface area of this Gaussian surface that we've drawn. R of this Gaussian surface is the 1 centimeter where we want to find this electric field. Epsilon naught is a constant, so on the right side. So Qn is the other piece we want to find. Qn is simply going to be Q1. That point charge is most certainly within this Gaussian surface, plus Q2, meaning however much charge is within this smaller sphere, how much charge is enclosed because of the charge density, rho 2. Okay, so charge density, let me go back to red to represent the non-conducting sphere. I need to know how much charge Q2 is within this smaller purple Gaussian surface that I drew, the closed surface we're talking about, the flux through. That is going to come by way of the charge density, rho 2, and the volume within the Gaussian surface. Because remember, charge density is charge per volume, whether that's total charge over total volume or a charge within a certain portion divided by the volume of that certain portion. It's the same because it's a uniform charge density. We know rho 2, we know the charge density that was given. V2 or Vn represents the volume of this Gaussian surface. So with radius of 1 centimeter. This is what I want to put in for my Qn in Gauss's law. Oh, wait, not completely. Sorry. This is my Q2. I forgot about the point charge. So let me fix over here. Qn is the point charge, which I have called Q1, plus the amount of charge within the non-conducting sphere is our charge density times 4/3 pi r cubed. Well, this is not going to simplify, unfortunately. So I will end up with the 4 pi epsilon naught and then r squared in the denominator. Plus rho 2. We can separate this out if we want. That would be fine. If we did that, we would have the Q1 over 4 pi epsilon naught r squared, which that hopefully makes sense. That's for a point charge. We have a point charge embedded in the center. The second portion, we would have the rho 2 4/3 pi r cubed in the numerator, 4 pi epsilon naught r squared. So here I could cancel a 4 and a pi. These r squares I could cancel. So this portion would become rho r over 3 epsilon naught. Make sure I didn't miss anything. Rho or, okay, I think I have it all. So moving that up just the point charge portion, I can do the 8.99 times 10 to the 9 for the 1 over 4 pi epsilon naught. The point charge is 5 nanocoulombs. R, this lowercase r, represents the radius of the Gaussian surface, where we're trying to find the field. For the non-conducting sphere portion, we have our charge density. We have R 0.01 over 3 epsilon naught. Now this negative sign here means that the electric field is pointing towards it. So we actually have the electric field pointing away from the point charge and then inwards for this non-conducting sphere, which will in turn cancel portions of each other out, which hopefully makes sense. If their fields are in opposite directions, that will decrease the overall electric field in that area. So let's go ahead and calculate this. So plugging this all in, the electric field strength at 1 centimeter from the center. I'm writing it in scientific notation because we don't want to have to count decimal places. So with 2 sig figs, if I've plugged it in correctly, I hope I have, is 4.5 times 10 to the 5th newtons per coulomb. Now, one other thing I want to make note of. Let's go back to blue on here. If they had asked for the electric field at a point where it was bigger than the actual radius of the non-conducting sphere, we would still find the Qn as a Q1 plus Q2. But Q2, when we take rho, its charge density, times the volume in, we would not use what we just did before, where we had rho 2 times 4/3 pi lowercase r cubed. So here, this is totally valid. The charge density times the volume is valid. The reason why we use this radius of 1 centimeter up here in our picture is because we only needed to know how much charge which was within that Gaussian surface we drew, which that Gaussian surface was full of charge. But if we're trying to find the overall electric field at a point outside of that, the Gaussian surface we draw would have to have a radius that is out here somewhere. Okay? So when we come back and say charge density times volume in, we have to use 4/3 pi capital R cubed, where we specifically mean the 2 centimeters, the radius of the actual non-conducting sphere. And that's because the charge is only distributed out to that 2 centimeters. There's no charge between the 2 centimeters, or outside of the 2 centimeters, I should say. So that would be the main difference between a point inside and outside. We would still just add those charges together, come back to our original equation of EA equal to QN over epsilon naught. So the charge enclosed or inside is ultimately what changes the most.